So in this video we're going to go over the matrix form of a system of linear equations in two variables. So this is the same three sets of systems that we looked at in the previous video where we talked about how the geometry of the lines drives the number of solutions that you get. So we're just going to take these three systems and put them into matrix form. So matrix form simply is you create a matrix. So I've got square brackets here, and inside of those square brackets you put the coefficients from your system. That's the first thing you do. So what you're going to wind up having is a column that is represents the x coefficients. You're going to have a column that represents the y coefficients, and then we're going to wind up with the column that has the constant terms on it. So you grab the first equation, and this first row is going to correspond to this first equation in the system, and we just look at the coefficients. So I have a 2 goes in the x's column because it's a coefficient on x, and this is really minus 3y is the same as plus negative 3y, so the coefficient is a negative 3, and the constant term goes last, it's a 7, and then you just grab the next equation down and do the same thing. Here the y and the x are not in the same order as they were before, so we need to be a little bit careful that this 5 goes in the x's column and this positive 6 goes in the y's column, and the 4 goes in the constants column. You don't usually write the x and the y over top of the matrix. You usually just construct the matrix without that, understanding that the first column is x, the second is y, or the first column is x sub 1, the second column is x sub 2, the third column is x sub 3, and so on and so forth. So this as a matrix would be 3, 4, 12, 3, 4, 12, 6, 8, 24. And I don't think I need to do this one, but what the heck. X's column, so 1.2 in the x's column, 0.4 in the y's column, 5 in the constants column. The x's column for the second equation we would get negative 1.5. And then I need to be a little bit careful here. In fact, probably easier to add 1.5x to both sides. So if we did that, we would get 1.5x plus 0.5y equaling a positive 2. So the x's column would get the 1.5, the y's column would get the 0.5, and the constant, when we're doing systems and putting them in matrix form, we always want the constants isolated on one side of the equal sign before we put things into matrix form. What was, oh, that was a 5, yeah. So get rid of the x and the y there. So a couple of final comments. If we had created the matrix with just the coefficients and not the constant terms, then we would have created a coefficient matrix. The moment we add the constant terms into the matrix like we did in each of these three examples, then we would call this an augmented matrix. This is an augmented matrix as opposed to just a coefficient matrix. So the coefficient matrix for this system would just look like this. It'd be 2, negative 3, 6, and 5. That would be the coefficient matrix. Coefficient matrix. And then a lot of textbooks, they'll write the augmented matrices this way. The convention that I learned way back in the day and that I like is to separate the constant terms from the coefficient matrix with the vertical bar. So when I do videos in this course, you'll see me when I'm working with an augmented matrix separate my constants column on the end from the coefficient matrix.